can do. It says if you have a voltage source, let's give it a value Vs for example, with the resistor here, let's give it the value R sub I for input, and this is attached to a circuit. The rest of the circuit I could care less what's going on there. I can, if I want to, take that circuit and take this source and that one and replace them with a resistor in parallel to that, and the value of that resistor will stay the same as this one. That doesn't change. But instead of a voltage source, I can replace it with the current source. And the value of the current source will be this one divided by that. Ohm's law. I equals V over R. These two circuits will be equal. Or vice versa. If I have a current source, I sub S, in parallel with the resistor, R sub I, and is attached to a circuit here, I could take this current source, change it to a voltage source in series with the same resistor. So the resistor doesn't change. What's going to change is that current source become a voltage. Well, V equals what? Ohm's law. I times R. So the value of this source is going to be I sub S times R sub I. That's really what source transformation is. You're going to see how this actually makes the problem sometimes 10 times easier. I'll start with an easy example, then I'll make it worse. So here's an example. I have a 9 milliamp current source. In parallel with 5 kilo ohm. On the top here I have 4.7K, another resistor of 3K, and a voltage source of 3 volts. And the question, what is I here? Now, if that was given to me in a problem, I can do mesh or node. It's really one equation by one unknown because I can combine these guys together. It doesn't affect I. I know the voltage here. That's the only voltage I don't know. So if I do node analysis, there's one node. If I do mesh analysis, I know what this current is, right? So that's the only current I don't know. So it's not a big deal with this one, but I'm going to show you how source transformation works. This one says if you have a current source in parallel with the resistor, and that's what we have here, I can change it to a voltage source in series with that resistor. So let me do that. I'm going to change that to a voltage source. I'll come back and calculate the value. The resistor value does not change. There's the 5K. 4.7K. 3K. And what's the value of that voltage source?
45.
It's 9 milli times V equals I times R, right? So the voltage of this, the value of this source is going to be 9 milliamp times 5K. The millis and Ks will cancel. You end up with what? 45 volts. And again, I can redraw the circuit by saying, oh, I got a 45 volt source here. I got one resistor on the top. I'm going to combine them into one. When I add them, 7 and 5, 12.7 is it? So now I can do a KVL or mesh equation right here. This is plus to minus. We know that current is I. There's only one current going through that. So negative 45 plus 12.7 K times I plus 3 is equal to 0. 12.7 K times I equals what? Is that a 42? What's I equal to? 42 divided by 12.7 K. .3 milliamp. This wasn't really a big circuit, so you could have done it mesh, nodal, or source transformation. It will not change anything. But let me give you a bigger one and show you after color source transformation how you can take that circuit now and make it much, much easier. Leave about half an inch on the top. There's going to be another layer on the top for this one. So here's my problem. 5 amps. Three ohms. 4 ohms. 7 ohms. We have a dependent source here. Current source, the value 3 times Vx. Above that source, we have another resistor with the value of 17. Two ohms, and this is Vx right there, plus minus Vx. Nine ohms, and another current source right there. 1. Now, if we decide to do this with nodal analysis, there's one node, I don't know the voltage here. There's 2, right? There's 3. There's 4. How many equations? 4 by 4 unknowns. Mesh equation. I know this current, so that's not unknown. 1, 2, 3. I know this current. So 3 equations by 3 unknowns. So it looks like mesh might be a better choice, but I'm going to do source transformation and hopefully eliminate 2 or 3 of these equations, or 2 of them. Make it 1 equation by 1 unknown, or 2 equations by 2 unknowns. Look right here. The question for this, find I, and I happens to be this current. So find I. I can do source transformation right here, and I can do one right here.
You can't do dependent sources?
Nope. Let's wait now.
So why would you want it to be a voltage
KVL.
Oh, why am I doing this one? Actually, let me erase this first, because I started writing again, copying the problem. What was the question? Why do I want to do source transformation? Why I want to change the voltage source?
Yeah, why do you want to turn it into voltage?
Well, I don't care about the voltage source, but if I put that resistor up there, what will happen? I'll be able to combine it with this. So I might want to do it more than once, and that's actually what I'm going to do here. So this is going to be a voltage source. What's the value of that voltage source, by the way?
5/3.
Not 5/3. V equals? Yep. What's I here? 5. And what's R? 3. So the value is 15. Notice the current's going upward. That means plus on the top, minus on the bottom. That's a 3. That's a 4. That's a 7. Three VX. Two plus minus VX I 17, and I'll do source transformation again. I'm going to put a resistor here of 9, and that'll be a voltage source plus to minus right there. And what's the value of that voltage source here? 9 volts.
And can you do, like, when you add up 3 and 4 on the left-hand side?
7?
Yeah, can you do that again?
Yep, that's what I'm going to do actually.
Oh, okay.
And then I'm going to do it one more time, and you're going to see that one will disappear. Now, let's see. I can't really combine these guys yet. Why? Because if I combine them, what happens to Vx? You lose it. But if I can figure out what Vx is in terms of I, because if I combine them, do I change I? Look at that current. If I combine them, I'm not changing I. So if I go Vx equals, what's Vx equal to? Based on my picture here. It's going that direction, and I is going that direction. That's 2 times I. Because as I travel in that direction, it's going to mark it plus to minus. And the value is 2 times I. So now I can take what I have here, and I'm going to redraw this multiple times just to show you. Take my time. I got lots of trees here. Don't worry. And now let's combine these also to 9 and 2, which is what? 11. I lost Vx, so Vx is gone. But I still know this is I. That doesn't change anything. It's the only complaint about this method. I keep redrawing it. That's the only complaint I have. Because now I can do another source transformation right here. Minus to plus, that means the current source going upward. Seven and 7. What's the value of the current source? I equals what? V over R. So what's the value? 15 over 7. 15 divided by 7. As I said, I'm going to redraw in that. Now I can combine these two resistors together because they're in parallel. And that will make it what? 3.5? Half of that number. You can do a couple of these steps in one, but I'm just going one at a time there. If I don't want to put this in terms of Vx, I can change it in terms of I, by the way. Right? Because I said earlier, what is Vx equal to? Because I don't have Vx here. People might get confused. Well, what is Vx? Well, I know Vx equals 2I. I can just write it inside that. Or go, this is 3 times 2I, which is what? 6I. I could do that. Maybe I'll do that. So I don't have to worry about the Vx there, because I already took care of it. It's gone.
How did you get the 2i?
That was an old one, right here. It's been sitting here. The current,
that's the
yeah.
resistance.
I can do source transformation again here.
I guess it's like easier to understand, and it's just more tedious.
We're just drawing. Let's see, got to multiply, right? Is that 7.5 here? You want to leave it 3Vx, you can. You want to leave it in terms of I, you can. And we said, what, 6I? Guess what? I can do source transformation right here with the dependent source. That's a current in parallel with that. Yep, I said be patient. Yep. I'm making my way to it. So now if I do that, I said, when we get to it, so I'm going to take that current source. Doesn't matter if you put the resistor first or the current source first. But that becomes now voltage dependent source. Notice the current's going to the right minus the plus. And what's the value for that one? 17 times 6. Is that 102? In series with a 17 ohm, 11 ohm, and 9. I'm looking for the current going in that direction. If I combine these three resistors together, does that change that current? No. So finally, the last picture I'm going to draw, 7.5, 28, and 3, what's that, 31 and a half, I think? You can double check that. I hope I'm not. 31.5. And now, can I solve for I? I have a KVL. Okay, let's see. KVL, let's assume the current is going to travel this way, because I is defined as going that way. So it's going to mark this plus to minus here. So here we go, KVL. I'll begin with this. Negative 102I plus 9 minus 7.5 plus 31.5I equals to 0. Sum of the voltage in a closed loop is 0. One equation, one unknown. 9 minus 7.5, what do we have? 1.5 here. What is 102 minus 31.5? It's 70.5 times I. Do we know what I is? 1.5 divided by that number. It's 0.021. Or you can say what? I equals 21 milliamp. If I know I can tell you what Vx from early. Vx is what? 2 times I, if I need it. 2 times 21, 42 millivolts. I don't know what they wanted to find in that circuit there. I assume it's I. Well, they never did it. But by doing color source transformations, we took that problem, we made it a little bit easier. Much easier. Even if you didn't go all the way to the end, even if I stopped short. Let's say when I get to this point, I decide I'm not going to convert anymore. Even right there, right? I go, well, I know what the voltage here, I don't know this one, I don't know this one, I know that one. It became 2 equations by 2 unknowns after color source transformations. If you went farther to this point, you don't know what this voltage, you know this one. I mean, you don't know this, you don't know that, you know this. Yep, 2 equations by 2 unknowns. Right here, you know this, you know this, you don't know this, you don't know that. It's still 2 equations if you do it with null analysis. If we do it using mesh analysis in this case, which is 1 loop, that's 1 equation by 1 unknown. Let me see if I can get another one quickly on this. Some ugly one, the back of the book. Yes.
Does it matter which side you put that 31.5 resistor or the
No.
dependence on?
No.
So the dependence-
You can move these guys around anywhere you want to in that circuit. It will not make a difference.
As long as they're in series.
Yep. So I can put these guys in top, put this one here, put this one there. How they connected, because people think, oh, it's going to push it there and it's going to travel. No. You can put them anywhere you want to, as long as they're connected in series, correct.
In the events, like if you have a circuit with parallel resistors. And
Yeah, it doesn't matter which one you put here, which one you put there.
What if there was a resistor that was like going across the top between 2 parallel resistors?
Then they're not parallel anymore.
Okay.
Yep. I'm looking for an ugly one. That could take a few minutes again, but that's okay. Maybe I can do color steps in one instead of doing each one at a time like I did with this. But it still wasn't really bad, it's just throwing it. That's the only problem. So another example. looks similar to that, it's just more stuff in it. I need something different. Maybe I can find something different. I want something that looks a little bit. Okay, I found one. I'm still looking for ugly one.
So, Professor, I have another question.
Yes.
When exactly will we be hitting integration and derivatives? Like
Integration toward the end, but when we get to RLC and RC circuits.
Okay.
Yep.
What about RC time constants? Do we get?
Yep, we'll get to that in chapter 7.
Okay.
7 or 8 hour book, 7 I think. Okay, let's take this problem. Now we have an AC source here. They have a value for, well, no, I don't have a value. So let's put a DC source for now. Pick a number. Go ahead. What do you want to use for a number here?
6.
6 volts, okay. We have 300 ohms here. A 1,000. I'm just making numbers up here. Uh, 500 ohms. Since I'm making numbers, I have no idea how small this value is going to be. This is 0.2 times Vx. I'll define Vx in a second. $1,000, 1K, and 2K, 2,000. And Vx, I'm going to define it on the top, plus to minus. And I'll make the question find Vx. I see a couple of things I can do quickly. What do you see? Combine these, good, on that end. And what else? Source transformation here. So maybe I'll do both of these. This will be a current source. I equals V over R, 6 divided by 300. And what do we have? Is that 0.02? In parallel with the 300 and the 1,000 here. As I said, when you make numbers up, sometimes because I wish I picked a different number. That's 0.2 Vx. Vx still good. I didn't damage it yet. And we have the product over the sum. 2 divided by 3 is at 667 roughly. These two guys in parallel. I can do 300 times 1,000 divided by 1,300. 231. I said, you start making numbers, your number is going to be funny there.
The dependent with the 667?
Okay, yep. You want to do what, source transformation?
Yeah.
I can do that, and I can do one here too.
So you can do those two dependent sources.
We just did that in the previous one, yeah? Yep, top one. Remember that one? Uh-oh. Now I get me messed up here. I think I flipped the pages in the wrong direction. No, they're good. Okay. Let's see. This one's going to be a voltage source pointing upward, plus on the top, minus on the bottom. 0.02 times 231. 4.615. How about 4.62? $231, 500. This is Vx. Now I can put that resistor here, 667, and I can notice the arrows here go minus from the bottom to the top, so it's plus on the top, minus on the bottom. Of the value of that, what's 0.2 times 667?
133.4.
Yep, 133.4 Vx. 0.2 times 667. V equals I times R. Thank you. I can take this resistor and this, put them together. It doesn't affect Vx. So if I take the 231, 667, 231 plus 667, that will give me one resistor of 898. $898, 500. Oh, that's a dependent source, wasn't it? Yep. Sorry, that was a dependent source. And this is 133.4 times Vx. And again, this is Vx. So if I define my current going this way, this is I, then what is Vx equal to?
Oh, 500 I.
Yep, 500 times I. So if I do KVL right here, it's only one loop. Minus 4.62 plus 898 times I plus 500 times I plus 133.4 times Vx, and Vx is what? 500I equals 0. How many unknowns in that equation? 1. So 4.62 equals 500 times 133.4. Add to it the 500. Add to it the 898. And with these stupid numbers I used there, 68,098 times I. What is I equal to? 4.62 divided by that number, which is 0.68 microamps, is 6.78 times 10 to the negative 5. Actually 67, right? Not 60. So that would be 67.8 times 10 to the minus 6. That's microamps. Yeah, it's going to be a tiny voltage. So what's Vx? 500 times 67.8 micro. And we got what? 0.034. Tiny voltage. Not a bad way of doing it, actually. That source transformation is a very popular way because you can drop a lot of equations if you do color source transformation. Even if you didn't do it from top to bottom, even if you did just color source transformation like here, you could have stopped here, 1, 2. And you could have done what? Nodal analysis, 2 nodes. If you decide to do a mesh equation, you know what this current, 1, 2. 2 equations by 2 unknowns instead of 4 by 4. If you start from the top, you know this, there's 1, there's 2, actually there's 3. That's all you have to start with. Okay, so that's source transformation. We also have color more techniques. Well, actually, we only have one more technique, and that's Thevenin. And after Thevenin, we do Norton. But Norton is nothing more than Thevenin with source transformation done to it. What Thevenin said, I'll wait on that actually till the next video, next class. And I'll do that separate.